In systems programming languages, we get direct access to memory. And we can use the address of operator to ask for some given variable or index of an array or something like that. What is its address in our virtual memory space? And we also have this concept of a pointer, which is a data type that allows us to store addresses of memory in variables and pass them around as a strongly typed value in our programs. So let's take a look at addresses in pointers. We're going to be exploring a process's address space in this course, and we're going to do so in a way that feels kind of like a video game where you're in a character who's exploring a map and you don't yet know what all exists in the map. We've kind of blacked out everything here, and as we reach new segments of memory, we'll unveil them and explore sort of what their use is and why we have them. I'm going to point out that the low addresses of memory would be where you imagine, if we imagine every address of memory has a numerical value associated with it, like its address, then the lowest numbers would be at the bottom and the highest numbers would be at the top here. As a reminder, a process is a running program or a program in the midst of execution. And many different processes can be running the same program. But we're thinking about, in this case, the memory of a single process. Each process has its memory isolated from others in a really clever and fascinating way called virtual memory. And this concept is a little bit beyond the scope of what we're looking at today, but virtual memory is an abstraction that our operating system gives us that allows processes to believe they have access to a wide range, like the entire range of a computer's memory, independent of all the other processes that are running. And somehow the operating system provides this abstraction such that you really don't have to worry about other programs in their memory space. The isolation is nice because this also leads to some protection. And if you try to do something in your program that accesses memory out of the bounds that it's been allocated and that it's requested from the operating system, there's some protections in place to prevent you from accidentally doing something you shouldn't be, or more importantly, from nefarious programs from hacking in certain ways. One of the common errors that you might see when working with pointers in memory is a segmentation fault. And this is the idea that you're trying to access memory outside of a segment that you should be at any given time. And so as we look at different segments, we'll see what are the segments and what might we have access to. And if you try and do something outside of that, and you'll see segmentation faults all the time. If you make some error in arithmetic when you're working with your pointers, it's not uncommon. Your program will crash with what's called a segmentation fault, and that's a very confusing name. If you don't know that what we're talking about is you've just accessed memory you shouldn't have yet, or shouldn't have at all, and the operating system takes care of that. Virtual memory is one of the key big concepts of operating systems, so we're going to leave that for an operating systems course, but it gives us this nice abstraction. Because we do have direct access to memory in C and in systems programming languages in general, we have to be very careful about how we use that, because there are some dangerous things we could do that we couldn't do in other languages that have managed memory systems that prevent some of the types of errors or bugs that we might see in a systems level language. I should note, just as a footnote, processes can share data between memory between two processes, but both processes are going to be intentional about doing so, and that requires some operating system intervention. So we're going to be exploring memory, and the first place we're going to look at is the call stack. And the call stack is one that you should be familiar with in this point in your programming career. You know that as function calls are made, frames are added to the call stack, and when function calls return, they're removed from the call stack, but really we just assume that the top of the stack, which winds up when we arrange the stack in this way. Notice one of the things we're doing is we're saying that the main frame, or the frame 0, the first frame in our program, is the highest in our stack. And as we push new frames, we're actually growing down our memory addresses, even though our stack is growing in this direction. So the call stack grows down in memory. And we'll talk about some intuition as to why this winds up actually being a nice feature in just a moment. It's ultimately an arbitrary decision. The people who made, I shouldn't say it's an arbitrary decision, it was a designed and intentional decision, but you could have chosen a design of a system where you had the stack at the bottom and what's at the bottom at the top, or use some other conventions. But this is what the world is effectively settled on as the leading design and where the call stack will go in a process. Each function call has its own frame, and the purpose of a frame is to provide some isolation so that you can have local variables in your functions. And when you call functions, you don't really need to worry about your local variables accidentally interacting with each other in ways that you don't expect. This is also central to being able to have recursion, right? Where you're calling the same function many times. And the key computational trick for pulling that off is we're adding new frames to the stack. Even though it's the same function, the local variables for each frame can be different. And that's how we can implement recursion on a call stack. The frames are not only going to have local variables, but they're also going to have the arguments that were passed to a function. The frame is going to have to keep track of where it returns back to. So which instruction is it going to jump back to once the function call is complete? And there's going to be actually some space that is shared between the calling frame and the callee, the caller and the callee. So there's going to be some space in the middle where once the function has decided or figured out its return value, it will drop that there. And then when the control returns back to the callee, the caller, that's where it will be able to access the return value, and the program will pick up from there. The mechanics of function calls in a systems language and at the systems level and at the instructions level actually are pretty nuanced. And so that's actually going to be subject for the next course, which is more about computer organization. We're going to use sort of this level of abstraction because there's some other things that the CPU itself needs to keep track of that will be stored in these frames as the program moves into and out of function calls. So the address of operator is the ampersand, and you put it before a variable or a value's name, and it will tell you, it will evaluate to the address of that particular variable in memory at that point when the program is running. So we can consider some code here where we have a main function, and inside of it we've got 2 character variables set up to be A and B. And what we're doing is we're just printing the address of each of those. And so the way that you would read this symbol is the address of whatever comes after it. So in this case, we're talking about, the address of A. And in this case, we're talking about the address of B. Right? So this is where we're going to drop, we're going to actually go evaluate what are the addresses. And the %p format specifier in printf is how we're able to print a pointer. So the address of is effectively a pointer, how we're able to print that to standard output or wherever we want it using the printf format specifiers. So the output of this, as we can see, is a very large hexadecimal value. And if we think about what this number is, thousands, millions, billions, trillions, 140 trillion is what the output to the right is the address of where the A and B variables are being stored, and then there's a little bit more specificity beyond that. A key thing to recognize here that's very important in understanding how pointers wind up working is notice that the difference between these 2 addresses, everything is the same, right? 7FFF, D5, 45BD, 1. So everything is the same except for the very low order bits here. And we're increasing this value by 1. And we do that because the memory address that's needed to, the memory space needed to store a character is 1 byte. And so A and B can be located 1 byte apart from each other because each of them only needs 1 byte of space. You'll also notice that A is lower than B, and the intuition for that is as the compiler is coming through and figuring out what are the variables in my function, the local variables that I'm going to need to establish space for within a frame. It's just keeping track of those in the order it sees them, but it might choose some other schemes, and it might choose to do something differently when there are arrays. In this case, A is 1 byte lower than B, so it's putting A in a lower position on the stack frame. The key takeaway of this is not necessarily specifically that A came before B or vice versa. The key takeaway here is that these are very large memory addresses, and it gives us some confirmation that in fact our main frame in memory is a very large number. It's not something that's closer to 0 and in the lower end of our virtual memory space, right? So we can try actually, and I would encourage you to try reproducing this program and running it. And it's going to have a peculiar result when I run it multiple times. So I've got my address of example here that is exactly as the slide showed. So I'm going to save it, and I'm going to gcc w all w extra g and standard C11, the name of the file. And now I'm going to run this. Oops. And when I ran a.out and asked that compiled program to become a process, and then the process was running, it printed out 86 and 87 as the lowest order bits. And notice that everything up until that was exactly the same. Now you're going to see a different output, and each time we run this, we're actually going to see slightly different outputs. You'll notice the high order bits are not changing, but there's some of the middle of the address is changing, and it seems to be somewhat random, and it is. We'll talk about why in just a moment. Before we get to why those numbers are not always the same each time we run that program, I would encourage you to pause the video here and think about the difference between these two functions, these two code snippets. The output of the code snippet on the left is shown, but not for the one on the right. And what I think you should try doing is imagine what would the output be on the right, and go ahead and commit to a response there and respond on Gradescope. The widths of types are going to influence the addresses of variables related to one another, right? So if we're using a uint16, that's going to take 2 bytes for each of the variables that are uint16. And in doing so, that means that it needs 2 bytes of space so that the next variable after it better start at an address that's 2 higher. Otherwise, you would be losing, potentially overwriting some data. So in this example, in the first example that was on the previous slide, we have 2 uint16 variables. A is initialized to 1, B is initialized to 2. And if we tried running this in our program, we would see that A's address might have a low order value of 0, and B's address might have a low order value of 2. And the reason why this is, like with bytes and chars, we saw that was only 1 difference between subsequent variables in memory. Well, with uint16, the spacing between, or the amount of space each variable needs is 2 bytes, right? And so this is why we're seeing the output that we are in the first example. So the type of a variable is going to establish its width, and that's going to tell you, and what it's telling the compiler is this is how many bytes of memory are needed on the frame of in a stack in order for this automatic variable to be set up when the function call begins and to have space for it. Even if there are some variables that are less than 1 byte, when there are variables that span more than 1 byte, they're going to take multiple contiguous addresses in memory. You're not going to have like an 8-byte, 64-bit integer that's spread off, like here's byte 1, and then 3 bytes later there's byte 2 and byte 3. They're all going to be contiguous back to back to back. And by convention in C, the address of a variable is going to be its first address in memory, and its first address would be its lowest. And that's kind of strange because due to little endian, which we've talked about just briefly before, due to little endian arrangement of values, you'll notice that the high order bits then are going to come after the low order bits if we're thinking about this as we move up the stack into higher and higher addresses. Underneath the hood and in C, it's taking care of all of these concerns for us, so we're not having to be too worried about it. But the intuition for why does the stack grow down has to do with little endian, right? And so if we visualize the stack growing down on a little endian machine, it's much easier to read these bytes, right? So when we try and read this pair of bytes, we see that, okay, it's all zeros, and then the low order bit is a 1 in the 2's position, so B is 2, and same with A, but A is 1, right? And so that's one of the intuitions behind why it's nice if we're visualizing the stack and thinking about this, that when you look at the contents of your memory, by virtue of being little endian and organized in this way, when we're growing from the stack down, we can read the contents of our memory a little bit more easily, right? Variable names are for humans only. So what we're seeing here in this column, this is just for our purposes. And if we compiled with debugging symbols, yes, there would be some debugging symbols for what our variable names were built into our binary, but that's really just for GDB to work. The actual program that's running the computer as it's running that process would not be concerned at all with where A and B are or what they even are. And so with variable names, what you're seeing here is we're saying when this function caller is evaluated, it's going to have established these two variables automatically for you in the stack frame, but the variable names A and B aren't going to be present in the machine at all if we're not debugging. All right. So with B, or with the second example, we were using uint32s, and notice that that's going to, each of those values is going to take 4 bytes. And that means the low order bytes are at the first address, at the low address, and at the high address, we have our high order bytes or bits. And that means A and B are going to be 4 bytes apart from one another if you were to look at their addresses. So why did the outputs of the addresses change each time we reran the program? Well, there's a feature built into our virtual machine's operating system, or your host's operating system, called ASLR. It's very different from ASMR, right? So this is address space layout randomization. Address space layout randomization. And the idea is, because with these systems languages, you have direct access to memory addresses. If someone were trying to hack your program and were able to insert some instructions, and the data for like where certain things in your program was stored was always at the same space whenever in the virtual memory space each time your program ran, it would be much easier to hack your program. But with ASLR, it's when your process begins, the operating system is choosing at random where each segment that's important when the process loads, what the offset will be, and then it runs from that position. And so this is actually something that you've seen without knowing it, when one of the ramifications of without knowing it, if I were to run gdb.a.out and run this program, notice that there is this warning here. It says error, disabling address space randomization, operation not permitted. So this is one of the trade-offs of developing in a container like we are with Docker. Address space randomization is a part of the host that's running the Docker system, and Docker isn't able to change that at on a per container basis. That winds up being a feature of the operating system and is a little bit more detailed than we want to get into now. But this gives you a sense of why that warning will show up, and what it's actually talking about is this idea that when your program runs, the computer and your operating system more specifically is choosing at random some memory address to say, okay, this is the start of where the call stack will be, for example. All right. So there's a little bit of randomization within there. We're not going to try and illustrate that in our diagram. We'll just assume that there's a fixed position. And if you were running GDB on your host system, like if you had a Linux machine and you were just developing straight on that, you could run this program such that it wouldn't try and randomize for debugging purposes. So the next question I want you to think about and pause the video in looking through is this one. How are addresses of local variables related through multiple stack frames? So consider this program, and we're defining a function named sum that is given a single parameter x of type uint64. And the first thing this function does is it prints x, and this %lu is for long unsigned, which is what we need to print a 64-bit number on this machine. And the p is once again for a pointer, right? So this is going to print x's value and the address of x, because that's the second positional parameter we're giving to the printf function, right? And then there's just a recursive implementation of a sum function, right? So where if the base case is if x is less than or equal to 1, we return x. Otherwise, we're going to recur. We're going to call sum on itself with an argument that's 1 less than x currently is, and add that to x. And so we're recursively computing a sum here. And from main, all we're doing is calling that function as part of a statement that is printing out whatever its return value is. So I want you to try thinking about the responses that were assigned on this particular question. Pause the video here, and we'll come back and talk briefly about this without giving it all away. All right, so a key idea to remember is if we're thinking about the call stack, we've got our main frame, and then when this call to sum occurs, that would set up another frame, sum, and it's going to have an argument x that is 3, right? And that 3 will be assigned to the parameter inside of the frame for sum, and we would print out the address and x, and then when we reach this line, we would once again have another frame for sum, and so on, right? Until we reached our base case, and then we would return back to the higher and higher frames. And each time we return back to the higher frames, it's as if we're deleting the previous frames which came before it, right? And as you remember, the call stack starts from a high memory address and grows in a downward fashion. So each frame is growing down on the virtual memory space in terms of its address. All right. Pointers are the idea that we can have a type in our programs that refer to an address of memory, right? And these are going to, since they are a first-class data type, when you hear something that's a first-class type in a programming language, that means you can use it to type variables, to type parameters, to type return types, and so on. We can store an address inside of a pointer, and when we dereference that address, that means, hey, don't read what's the pointer's value, which is just going to be an address, but actually go look up where in memory, what is the value that the pointer is pointing to. So what is the point of pointers? Why haven't you needed them before? If this is your first time in a C or C family language where you're dealing with direct access to memory and pointers, you haven't needed these before. Well, that's actually not entirely true. In Java, you have needed them before. You just didn't quite realize it because the details of pointers were sort of abstracted away. And you did have to learn some of the peculiar rules that were differences between primitive types and reference types, or value types and reference types, right? Whereas value types were stored on the call stack, reference types were stored in the heap, and you could have multiple references to the same object or the same array in a language like Java. And the idea of those references, if you imagine in Java a frame, like I'll just make a main frame, and let's say we had some array A that referred to an array on the heap, right? And pretty soon we'll learn where the heap is in memory. This is our stack. We could also have a reference B to that same array on the heap, right? When we've drawn these arrows out in an intro programming class, we've tried to visualize the significance of them. But what we're going to see is if we actually wanted to think about, well, how does this work in C? We know that we've just got this one memory space and we haven't seen the heap yet. And I'm going to give something away a little bit to say that the heap comes towards the bottom of the stack in a lower area, or lower segment than the frame. So this is, the pink is going to be sort of how we've waved our hands and visualized this in earlier classes. But a preview of where we're going is somewhere down lower in our memory space. We're going to have an array that takes up heap space, and that will be, if this is all our virtual memory, the heap would be somewhere down in this segment. And what A would be is we could think of it as a pointer, but what it actually is, because you can't have arrows in your memory, is, let's imagine this is like address 6F. Right? And actually in C, the address of the would be the first byte of our array. So let's say 6F is the starting address of this array. Well, A would have a value of 6F in it, and B would have a value of 6F if we were thinking about pointers. And so what a pointer is, and what an arrow in our memory diagrams, and we wouldn't have this over here because the heap is actually in that same vertical, in our same address space. A pointer is really just an address in memory. So where you've drawn arrows before, that's really just a number. That's the location of some other location in memory. And in a language like Java or Python or JavaScript that's managed, those references are happening automatically as you use the new keyword to say, give me a new array or a new object. And your variables are actually just storing the addresses that refer to some other location in memory. And then when you go and use those addresses, like like dog Fido.bark, right, or Fido.name to access some attribute, or array subscript 2, behind the scenes, Java is dereferencing that reference, that pointer, and looking up some value somewhere else in memory on the heap. Right, so that's a little bit more of a diversion than I was hoping for here. But the point is, you have actually used pointers. The details of them have just been abstracted away in the languages that you've used. The reason why we use them and why we have them and why they're valuable is because as we start writing more complex programs and have larger data structures and larger arrays, it would be very inefficient if we had to copy the entirety of those data structures into a function and return and copy everything back out of a function each time we wanted to make use of it somewhere else in our program. And so what a pointer gives us the ability to do is much more efficiently just pass an address and says, hey, here's where the data that you're going to manipulate or read from or calculate something on is located. I'm not going to give you all of that data though, right? And so it's a much more efficient way than trying to copy a large data structure. And that's primarily its purpose. But there are other use cases that we'll see. There's some really clever ways that we can iterate through an array using pointers. We'll see that if we have an array of pointers to, say, strings or other larger objects, we can sort that array of pointers to have a sorted handle on all of our objects or our strings, right? And lastly, we'll see there's some clever ways if we wanted to implement something that feels a little bit like higher order functions, where you can pass one function to another function and it can use that function inside of its body. Well, in order to do that, we're going to have pointers to functions, which is how we'll have dynamic dispatch later on in the course. So let's actually try getting some notes in a file and practicing working with pointers. And I would encourage you to go ahead and set up a file named pointer demo somewhere in your container. And let's work on this. I named mine with 01, but you don't need to prefix yours with 01. You can just name it pointer demo. I've gone ahead and included standard IO, and that's all we'll need for this particular program. Let me make this a little bit bigger. All right, so let's go ahead and just set up a byte, something like a character, and assign it a value Z. So nothing fancy here yet, no surprises. We can set up a pointer to this character by saying char pointer, and we'll talk about this syntax specifically. A char pointer, I'll name it something slightly different because this is just the name of the variable, is assigned the address of a char. Right? Let's maybe just go ahead and set up a note here. Maybe we'll say we're declaring a pointer and initialize to address of a char. All right. So we've set up this pointer, and we should talk about the syntax. The asterisk that you're seeing is what declares a pointer type. So we're saying char, and then followed by an asterisk says this is a pointer. One of the really funky syntax decisions of the C programming language was that this star can either be closer to the variable name or closer to the type name. So there's no difference between what we've just written here and that, right? So the white space doesn't really matter. We're saying this is a character pointer. The way that the book encourages you to read one of these declarations is actually backwards. And I actually think this is really clever. I wish someone had taught me this earlier in my career. So what we're saying is it's a pointer to a character, right? So a char pointer, its type is a pointer, that's the star, to a character. And that's how you should read it. And we're initializing it to the address of a char, right? So next we might go ahead and print out this address. So read, print the address in the pointer, right? And how do we do that? Well, printf, and we can say, okay, a char pointer is, and then we're going to use the p format specifier, and a char pointer. And let me add in semicolon after that. Cool. So we are printing out the address of this pointer. So this is actually what's stored in the variable a char pointer. But what if we wanted to read the contents that it was pointing to? So we wanted to print the character that was stored in a char, because a char pointer stores the address of a char. How can we actually read what it points to? So let's go ahead and add that as well. So read the address referenced by the pointer. And I'm gonna say dereference is what you would call this. So we can printf and a char. And I might actually just, to make this a little bit, the output of this more sensible when we're looking at it, say asterisk a char pointer. And since we're printing out a character, right? Since we're going to be ultimately printing out, it should hopefully be z if this all comes together and makes sense. We're going to use the character format specifier, and we're going to dereference, which is once again this asterisk. So you're seeing this asterisk used in two ways. The first way was we're saying this is a pointer to a character. So when we're declaring a type in conjunction with this asterisk, it's indicating that we're working with a pointer type. When we use the asterisk before an identifier, so notice this is going to be an identifier, and in this case a char pointer, that is a pointer variable, then or a pointer value, then what we're saying is read the address that is stored, go look up and read from the address that's stored in this pointer, right? Cool, so I'm saving my file, and with that I think we should go ahead and try running this. So I'm going to go back to my console and clear my screen real quick to get that weird coloring away. And GCC, WALL, WExtra, standard, C11, debugging symbols, and I named mine O1 pointer demo. You probably just named yours pointer demo. And so now if we say ./a.out, notice that when we printed what was the contents of a character pointer as a pointer, we could see the address of it. And if we printed what was the dereferenced value stored in a char pointer, notice that z was the value that was stored there, right? If we wanted to visualize a little bit of what's going on here, we can think about this as, okay, we've got a frame main, and a char is going to have the character z in it, and a char pointer is effectively a reference or a pointer to the a char variable, or the a char location in memory, right? So, but what we just looked at was, well, A, variable names are fake, and B, pointer arrows are also fake, so there must be something slightly different here. And sure enough, these things wouldn't actually be visible if we looked in the contents of our memory. The program is just going to have a frame for mains variables, and this was some like long variable name, 02, right? And so if this was the 02 address and this is the 03 address, or actually we're counting down, so this would have been the 01 address, and I've got other issues if I'm thinking about it in this way. Let's fix those. Okay, so if we're thinking about how this frame would have been laid out, like we were seeing before, the pointer value would have come second. So let's call this address 02, and at address 01 in the main frame. And of course, there's like all the rest of the beginning of this address. These are just the low order bits. This is where we would have had the character Z, all right? And 02 would have stored a reference to, or the address of, the 01 address. And of course, because this is, as we'll see in just a moment, a pointer type needs 8 bytes in a 64-bit machine. So this pointer would have actually, its data would have been spread out over the memory address 02 through 09. All right. Let's actually add one more example here. I forgot, getting carried away. Why don't we add an example where we can write to the memory address stored in a pointer. So here, if we dereference on the left-hand side of an assignment statement, so dereference a char pointer and assign that y, we can do that. And what I might do is just go back up and copy with YY, so yank for the whole line, and then go and press P for paste. And I need a closing semicolon there at the end of my line. What we'll do is we're saying, okay, in the memory that is pointed to by a char pointer, so we're going to go update effectively this variable a char, assign y. And I actually think this demo is more interesting if we say, okay, read from a char. And let's not, we'll update our printed label here so that we're saying print from a char, and we'll just read a char, right? So notice what we're saying here is update the memory that is pointed to by a char pointer to have the contents, the character y. And then we're going to see, well, did we actually change the variable a char? And let's try it out. So I'm going to save this and run this program one more time. And notice that a char, when we accessed it, changed to y. So sure enough, by taking out a pointer that referenced a char and then updating that through dereferencing, we were able to change some other local variable's value. And that's pretty scary, right? Like that's something that if you saw this in Java, you would probably panic a little bit because this isn't possible in Java. One of the things that we've said in 110 for a number of years now is you can never have in Java or Python one of these references or a pointer to somewhere on your call stack. Well, as we're seeing here in C, you absolutely can have a pointer to a local variable, and then through that pointer, you can change that local variable. So now we have multiple ways of doing that. I want to point out, and I'll say this later in the slide deck, that some of these examples are a little bit contrived, and they don't give you a good reason for why you would want to do this yet. This sort of feels like, why would you ever need to do this? And you're absolutely right. Like if this was all we were doing, this would not be interesting. But if you can imagine, we could pass that pointer or that address to a function call, and the function call could then change some other variable. That's actually winds up being very valuable and something we'll be doing frequently as the semester goes on. So just for reference, there's a slide here that has some of the common operations that you'll need to be able to do, the common operators and operations on pointers. These are all ones that we looked at in the previous example. So what does this actually look like under the hood? Well, we tried to illustrate that with a quick diagram before, but if we try to visualize this in memory, notice that because we declared a char first, and we're just assuming that when we declare a variable before another in our frame, that it's going to come at a lower position in the frame on the call stack. And so a char might have been here, and this would correspond to the Z character if we were look at its contents in ASCII. But this is just the hexadecimal encoding of Z. And then what's really cool and actually kind of crazy is if we imagine, well, what does a char pointer look like? Well, again, because we're working in a 64-bit system, that means the addresses of our memory in our virtual memory space are going to be 64 bits wide. So in order to store an address, we need 8 bytes of memory to be dedicated to it. And so a-char pointer, if we were to look at it, you would notice that it's 7f, fe, 5f, e1. And that's the address of a-char, right? 7f, fe, 5f, e1, 8d12, 8d12. And so what a pointer is doing is it's using 8 bytes to store the address of some other location in memory. And that feels kind of crazy when you see a pointer to an individual character, when that individual character only needed 1 byte for its storage. But we'll see that typically we're taking out pointers to data structures that are much larger than 8 bytes, like larger arrays or larger structures. And so this winds up being an okay trade-off that we shouldn't really worry about. You'll notice that the high order bits of this pointer are 1'd out effectively, sign extended with 1. On modern machines, we don't actually use all 64 bits yet. We only use 48. 48 bits, you can access up to 256 terabytes of memory, which is way, way, way more. In fact, 16,000 times more, over 16,000 times more than your laptop has in it. So it's a long time before a system that we're using today is going to run out of memory, but when we do, if we do in the future, maybe in your lifetime, we'll use all 64 bits of address space. But the big idea is that the address of A, and that's what I've highlighted in purple, right? So the address of A's contents in memory is what we're storing in the contents of a-char pointer, right? And that's the big idea of what a pointer is. It's a reference or an address to somewhere else in your program. In your process, I should say. So I've got another challenge question for you to think about, and we're not going to work through this together, but I do want to point out what is interesting about this and give you a little bit of a hint as to how to think about this. So notice we have this add1 function, and we had a declaration of it at the top, and then we had the implementation or the definition of it down here at the bottom. And what we're doing is we're giving a pointer to a character, right? So again, we read this backwards. So char pointer is a pointer to a character. So we're giving an address to a character to this add1, and then what we're saying is look up what the current value stored in that address is, add 1 to it, and then store whatever the result is back in the address that was given to us, right? So with that knowledge, try pausing the video here, working through this, and then we'll come back to it after you're done. All right, so the key interesting thing that's happening here is we are actually changing a variable that is local to the mainframe from add1. This is one of those things that was never possible before. And if it feels uncomfortable to you, I would encourage trying this out and getting a handle on it in your editor. So pointers can also be used as parameters, as we just saw in that last example. And this gives some other function and some other function call in that frame access to some other memory it wouldn't have otherwise had, right? We were giving access to a local variable in main to some other function call. So main's local was accessible from outside of its scope, and we could change it from outside of its scope. And if that sentence doesn't scare you a little bit, keep rereading it, right? The idea that you can have a variable that can be accessed from outside of that variable scope by passing a pointer to it should be very concerning to you. And this is a source of many bugs, and we have to be very careful about this. And we're gonna think critically and apply some common techniques for trying to avoid common errors that you'll encounter if you're using this very loosely. Right? But this idea that you can now access a local variable from outside of its scope is both powerful and horrifying. You've seen being able to access and have references to other values before with heap values, right? With objects. When you pass around reference types in Java, you're giving someone else access to that exact same value, but you haven't seen this with local variables. And with local variables, because they're on our call stack, and remember, after a frame has returned, you have no guarantee that its memory is still there, and you should treat any memory that was local to a function call and in that frame as invalid as soon as that function returns. So we might be able to access invalid memory in this way. And I would encourage you to try seeing if you can come up with an example of how you might do that by, say, returning an address in memory from a function. And you'll see that that's kind of scary that you can do that. And this is a source of both bugs and and an opportunity for many hackers to do things that are kind of nefarious. So where we actually do make use of this for good and for a good purpose is when we're writing object-oriented style C, and I've got that in quotes because C doesn't have true objects. But just like in a language like Python, where you're being explicit about a method and having to define what is the self, which is like this in Java, with C, when we have object-oriented style C, we'll have to set up a parameter that will be a pointer to some object that we'll typically call self, that's very much like the this variable that automatically exists in methods. And so we'll see this as a valuable technique. This is also how we'll wind up making use of the ability to pass arrays around into functions. So we've got one more example here. We're setting up an array, and we're setting up an array named A with 4 characters in it, COMP. When we print off the first 2 values, we're actually printing off the addresses of those values. And so my question to you is, if we know that C is going to store the address of the lowest byte or the first byte of some value, and the first byte of this array A is stored at a memory address that ends in 4, what would you expect the address of the index 1, the index 2, and the index 3 values to be? How are they related to one another? And the next question is, there's this really funky looking little bit of syntax down here where we're saying, what's the address of A's second element, or its index 1? And when we add 1 to that address, what happens? We print out that value, so we're going to be printing out whatever is dereferenced by this pointer, and then we're subtracting 1 from that and printing out whatever that value is. So this is an example of what we call pointer arithmetic. And I would encourage you to pause, see if you can work through this, and imagine what the results are, and then give this a shot in your editor as well. So let's talk about the really fascinating result that you saw if you tried running this, which is, it turns out we can perform arithmetic on pointers because these are just numbers, right? Addresses are just numbers under the hood with a little bit of extra context. We know what type we're pointing to, right? So if we're pointing to a character, that's 1 byte, so that we would know if we wanted the next character, it would be 1 byte away in memory. Whereas if we had a uint64, we would know that it would be 8 bytes away. And so if we add 1 to the address of a uint64, that's going to have the effect of adding 8 bytes to the address it stores. So the extra context that a pointer has is what type of data it expects to be pointing to. You can add and subtract integers from pointers, and this will have the effect of offsetting that address in memory from where it currently is. And you can subtract 2 pointers of the same type. And the reason for this, and the only place you're really supposed to use this, and the only place you're guaranteed for it to work, is if you have the addresses of 2 elements in an array, you can use those addresses for some clever arithmetic by comparing the addresses and doing subtraction with them to see how far apart they are. This will tell you how many bytes are between 2 addresses in the same array. When we're working with arrays, we'll see that this is where we typically use these tricks, where we can use a little bit of pointer arithmetic to move to some other element in the array. So like if we have a pointer to the first element and we have a loop, we could increase that pointer by 1. And because that pointer knows what type it's pointing to in each individual index, it would update it the correct number of bytes, and that would be one way that we could iterate through an array. We'll be looking at that concept in much more depth in the next lesson. As I mentioned, the arithmetic that happens when you add 1 to a pointer's address, you're not guaranteed for that address to only update by 1. It would if it were a character and storing 1 byte. But if you added 1 to an address that was pointing to a uint64, it would add 8 bytes onto that address. The address of an array in C, and arrays are something we're going to spend much more time with because their semantics are different from those that you've seen in other languages. But the array variable is actually a pointer to the first address of the first element in its items. And this is different than an array name is different from a traditional pointer because you can't reassign to an array's name. You can't have an array name reassigned to some other array. It just is what it is. Whereas a pointer, you can reassign and have it point to some other memory address after the fact, as long as the types match up. We'll look at size of later and those nuances in the next lesson. What's really clever and interesting about array indexing is that now that we have these pointers in our pockets, we have the ability to look at, well, what does array indexing actually mean? And we'll come back to this question a few times later as we look more closely at memory addresses. But array index I is the same, semantically the same. It's just sugar for dereferencing and then pointer arithmetic A, which is a pointer address or an address in memory, plus I, which is the offset. And because that offset is going to automatically take into account the width of each item or element in the array, this will calculate the correct offset of whatever the item is that you're trying to look up. You are dereferencing automatically when you are accessing an item in an array. So one of the things we can look at is we can actually set up pointers to elements in an array. So here we're saying we've got an array of ints named numbers, and we set up a pointer p that is going to point to the very first item 10. So when we print out what is p dereferenced, it would be whatever was at index 0. If we used here, if we had said what is p plus 1, even though this is an int and these numbers are going to be probably 4 bytes away from one another, it would have evaluated to 20, and p plus 2 would have evaluated to 30. Pointer arithmetic is one of those concepts that is very opaque and kind of confusing to begin with because it feels so different from what we've done before. So we're going to be spending much more time getting comfortable with this concept as we move ahead. So this is a quick introduction to the memory, the address of operator in C, which gives you access to memory addresses, and we can store those addresses in pointers. Pointers are just a type that allow us to store addresses explicitly as variables or use them as types to parameters or return types from functions. And we've got lots of clever things that we can do with them in C, but we need to be very careful and thoughtful about how we use them. And we'll be spending more time looking at different ways to keep track of our pointers and to think a little bit more thoughtfully about where we are using them and how we're using them.